A recent Gnostic vulnerability scan found 1,862 model context protocol servers fully exposed to the public internet. During their manual verification phase, the researchers tested a subset of these instances. Every single one permitted unauthenticated access to their tool listings. Anyone on the internet could query the server to see exactly what actions it was configured to execute. This exposure contradicts the design of the protocol. The Model Context Protocol, or MCP, already includes a formal specification supporting an OAuth 2.1 authorization framework. This chart tracks the scale of public MCP tool availability over a single year. We see roughly 4,800 tools in January 2025, spiking to over 177,000 by February 2026. Ecosystem deployment outran security implementation. npm package data recorded roughly 14 million server downloads. Look at their composition. The blue area maps perception tools, but neon violet shows a categorical shift. By February 2026, action-oriented operations represented 65% of usage, actively modifying external systems. The financial stakes attached to these actions are severe. As an outlier metric, MCP servers specifically equipped with payment execution capabilities grew from 47 instances to 1,578. We are watching a massive scaling event of autonomous execution surfaces. When these autonomous agents capable of financial transactions connect directly to unauthenticated servers, it creates a systemic, ecosystem-wide vulnerability. I'm Bearded AI Guy. Today, we are analyzing the Agent Identity Protocol, or AIP, based on a rigorous teardown published by the Human Architect. A common misconception among engineers is that deploying standard OAuth 2.1 makes an agentic architecture secure. Legacy authorization models were engineered for human-to-server interactions, one user requesting data from one backend. Modern agent-to-agent systems operate through complex, multi-layered delegation chains. OAuth secures the initial transport layer between 2 points. It structurally fails the moment an agent delegates its task to a second agent. When an orchestrator passes a command through multiple autonomous subagents, the final backend system has no mechanism to verify the cryptographic provenance of that original command. Securing these servers requires a protocol layer designed specifically for multi-agent identity, as simple transport security cannot bridge the delegation gap. Let's isolate the mechanical failure point of standard OAuth 2.1 within an MCP environment. OAuth excels at executing a single client's request to access a single protected resource server. The handshake is direct and finite. Now map that onto an autonomous workflow. An orchestrator delegates a task to a subagent. That subagent then sends a request to the external tool server. At this final hop, the tool server validates the access token of the subagent. The lock opens. But the server receives zero cryptographic data proving the original orchestrator's identity or the constraints the orchestrator applied to the task. If an attacker compromises that middle subagent, it retains valid access keys to the final tool server. It executes actions with zero accountability. Multi-hop provenance is structurally absent from the current standards. You cannot use standard OAuth to encode multi-agent delegation chains as a first-class verifiable audit artifact. Relying solely on OAuth for multi-agent workflows creates a silent break in the cryptographic audit trail, leaving your highest-stakes actions vulnerable to hijacking. The Agent Identity Protocol proposes a specific multi-hop delegation layer to close this gap. It introduces a new core cryptographic primitive, the Invocation Bound Capability Token, or IBCT. An IBCT is a single append-only cryptographic object. It mathematically unifies agent identity, attenuated authorization, and exact provenance binding into one package. The protocol establishes 2 wire formats. Compact mode utilizes an E25519 signed JSON web token. This covers single-hop operations with broad compatibility. The second format is chained mode, engineered specifically for complex networks. This utilizes biscuit tokens to handle multi-hop delegation scenarios. In chained mode, sequential data log policy blocks are appended to the token chain every time a task passes from one agent to another. This physical structure enforces the most critical architectural principle of the protocol, constraint monotonicity. Constraint monotonicity ensures that each new delegation hop can only narrow access scopes or reduce compute budgets. A downstream agent can never widen permissions. If a delegatee is fully compromised by an attacker, its execution authority cannot exceed the strict, narrow limits permanently stamped into the initial chain. IBCTs solve the multi-agent accountability crisis at the protocol level. They mathematically guarantee that privilege escalation is impossible across the entire chain. The immediate objection from developers is that running cryptographic chain verification on every single tool call will introduce massive latency in live inference. The micro-benchmark data addresses this directly. Compact mode verification averages 0.049 milliseconds in Rust and 0.189 milliseconds in Python. The token payloads are equally efficient. A compact token requires only 356 bytes of data. In real-world deployment experiments, an MCP over HTTP setup adds an overhead of exactly 0.22 milliseconds of latency compared to a baseline with zero authentication. Even in live multi-agent LLM deployments, the total additional latency sits at 2.35 milliseconds. Relative to the time it takes an LLM to generate a response, that overhead is negligible. Moving to adversarial security testing, researchers subjected the architecture to 600 specific attack attempts. The token chain maintained a 100% rejection rate. Chain delegation effectively neutralized attack vectors that bypass plain JWT deployments, catching strict depth violations and blocking audit evasion attempts utilizing empty context windows. AIP guarantees mathematical constraint enforcement at sub-millisecond overhead. You can deploy deep, verifiable security without sacrificing your system's operational performance. When we assemble these components, we see the complete protocol stack required to secure modern agentic systems. Layer 1 is the MCP tool environment. It provides the baseline infrastructure and the standardized action surface. Layer 2 is OAuth 2.1, providing the user-consented transport layer and the initial client-server handshake. Layer 3 is AIP. This caps the stack, enforcing multi-agent identity, strict provenance, and delegation tracking. The base of the stack is already heavily adopted. NCPD currently reports over 97 million monthly SDK downloads and sustains over 10,000 active public servers. That momentum recently culminated in the protocol being formally donated to the Linux Foundation-directed Agentic AI Foundation. AIP is in a much earlier phase. It exists as an alpha package on PyPy and an individual internet draft submitted to the IETF. While AIP is an emerging candidate rather than a formal industry standard, it provides the precise architectural blueprint required to secure an agent ecosystem scaling beyond human oversight. If this breakdown was valuable, subscribe to Bearded AI Guy for continuous AI architecture deep dives. For the engineers in the comments, how are you currently handling multi-hop delegation without native IBCT support in your stacks? A massive thank you to the human architect for their initial synthesis of the AIP papers that guided this analysis. As we transition to a world driven by autonomous delegation, remember this: if your system constraints aren't monotonic, the architecture is structurally unsecured.